Sometimes expressions might appear equivalent, but they may not be after all. How can you tell for sure? Look at look at y sub 1 and y sub 2. I was saying f because that's how it is in our calculators now, right? F1 and f2. Look at y1 and y2. Do those appear equivalent to you? Maybe or maybe not, right? So let's simplify them to see if we can figure out if they're equivalent. It's wanting us to show that they're the same by simplifying y sub 2. So if I have x over x squared plus 2x, what do you notice in the denominator of that fraction? What do you notice? No, I'm just talking about the denominator right now. What do you notice about the denominator? What do you notice about both terms in the denominator? They both have an x, okay? That means I could factor an x out of each term, right? So I have x over, if I factor out an x of each term, what's left? Very good, x plus 2. And what am I allowed to do if I have a factor in the numerator and the same exact factor in the denominator? What's 5 divided by 5? 1. What's 12 divided by 12? What's 356 divided by 356? So what's x divided by x? 1. So if I simplify that to 1, what do I have left? 1 over x plus 2. Now what did y sub 1 equal? 1 over x plus 2. Are those equivalent? Maybe. Maybe. I know, it's really weird, isn't it? So I'm going to go to my calculator. I'm going to create a new document that is a graph. Okay, I'm going to create a graph. Now I could put all these into a calculator just by hand, but wouldn't it be easier to go to graph, put the equation in y1 and look at the table? Wouldn't that be easier? Enough, please. So for f1, that's going to be my y1. So I need 1 over x plus 2. And then for my f2 or my y2, I need x over x squared plus 2x. Now graph-wise, do they look the same? Yes? Okay. So let's go look at the table. Control T. Let's look at the table. Alright, so when x is negative 2, it's y sub 1 says undefined, right? Now what word did we use to talk about this on Friday? Do you remember? An error, right? Are you okay with us using undefined today since that's what it actually says in our calculator? It used to say error in the old calculators, just so you know. Okay? So for y1, when x is negative 1, y is 1. When x is 0, y is 0.5. When x is 1, y is 0.3333, so that's really the same as 1/3, right? And then 2 is 0.25. Or 1/4, right? Let's look at y2 real quick. So when x is negative 2, y is undefined. When x is negative 1, y is 1. When x is 0, y is undefined. When x is 1, y is 0.333, so 1/3. And when x is 2, y is 0.25, or 1/4. Is that what you expected? How are the tables not equivalent? Yeah, they're not equivalent at x equals 0, are they? Well, then it says sketch the graph of y2. Well, we already know what the graph of y2 looks like. It looks like this, right? How many vertical asymptotes does it have? That was a good joke. How many vertical asymptotes does it have? 1. It has 1 vertical asymptote. does this match the information in the table? Does y sub 2 look like it should have one asymptote? One vertical asymptote? No, it does not. Something's weird. Okay? Probably Clay. Yeah, I know. Okay, look at number 4. We're gonna change to this equation real quick for number 4. Okay? Find the vertical asymptote of this function. How do we find vertical asymptotes? Yeah, you can either remember that or you could keep reading the question from where I stopped, right? Find the vertical asymptote of this function by setting the denominator equal to 0. So if I say 2x minus 6 equals 0, some of you can do this in your head, but we are showing our work. And I got x equals 3. You okay with that? Okay. Excuse me. So I'm going to go back to my calculator. And I'm going to put in this new function right here that we just talked about. It's a different one. Yeah. X squared. I could have put it in like an F3 or something, but I just don't want to be confused by those other two things that are there. So I'm putting in separately. 2x minus 6. What shape is that? Let's look at the table. So Control T. When x is 0, y is 0. When x is 1, y is 0.5. When x is 2, y is 1. When x is 3, y is undefined. When x is 4, y is 2. Does the table support the location of the vertical asymptote? Yes. Because of at x equals 3, right? But sketching the graph looks like that, doesn't it? What is strange about this graph? In fact, there's no vertical asymptotes. It's not even that you can't see it, it's that there's not one. Because this is what a vertical asymptote looks like, isn't it? Did we do anything wrong in our calculations? We didn't, did we? Okay. Usually values of x that make the denominator equal 0 will create what? An asymptote, specifically a vertical asymptote. However, or in their words, unless, wait, what does it make? The denominator equal to 0, right? That will give us a vertical asymptote. That's true unless the value also makes the numerator equal to 0. If it makes the numerator equal to 0 and the denominator equal to 0, both of those, it's not a vertical asymptote anymore. It's called a removable discontinuity. On our old graphs, you could actually see the removable discontinuity. You could see it. Okay? The pixels on these calculators are so much smaller that I can't show it to you anymore. Even if I zoom way in, you still can't see it because of the value of the pixels. Okay? I used to have a calculator that you could do it on, and then that calculator finally died because it was so old. Okay? What? No, I do not miss it. It's okay, but thank you for asking. So let's look real quick at this equation right here. First of all, let's factor both the numerator and the denominator. Well, if we factor out an x from each term, we get x minus 3. Then if we factor the denominator, what multiplies to be negative 3 and adds to be negative 2? Positive 1 and negative 3, right? Do you notice that in the numerator and denominator, they both have an x minus 3? Yes? That is when it makes both of them equal to 0, and that's a removable discontinuity, also known as a hole. Okay? This is what you could see on that other calculator. You could literally see a blank pixel. It's an empty pixel. Nothing is there. When we graph it such that we can see a hole. It's an open circle. Okay? But looking at this other one right here, there's not an x plus 1 in the numerator and denominator. It's only in the denominator. When we set that equal to 0, that is still a vertical asymptote. Okay? Now, come back over here real quick. Where's the hole? At 3. Could we look at these and tell that the hole would be at 3? How? If you set them equal to 0. That's exactly right. So to find the vertical asymptote, we set this equal to 0, right? How do we find the removable discontinuity? Set it equal to 0. We still do the same sort of thing. We have to be able to interpret whether it's a hole or an asymptote, a vertical asymptote. You okay with that? So, if you plug in an x value and get a number, God bless you, over 0, the graph will have a vertical asymptote. Okay? If you plug in an x value and get 0 over 0, what's going to be there? What is a removable discontinuity sometimes called? A hole. Okay? But you can't tell which one is which just by looking at the table in your calculator. Because the table is going to say undefined. I know it says error, but your table will actually say undefined whether it is a hole or a vertical asymptote. So to know for sure, what are we going to have to do? What? You can, but if we don't have a calculator to look at the graph, how are we going to figure it out? Okay, look, it starts with an F. I wrote an F there already. We have to factor. Okay, now I know how much you loved factoring, so guess what? We get to do it again. Yay! So here's 6 problems. Which 2 would you like me to do? Okay, 4. You sure?
No, actually, no. Jennifer, what did you think are going to be the hardest for us?
Honey, I can do all of them. 4 and 3? Okay, 4 and 3 are the ones I'm doing. So which ones are you going to do by yourself? 1, 2, 5, and 6. Are you sure? Okay, so which one are you going to do first, 3 or 4? 3. All right, so if we're going to start with 3, what should we do first to start? Factor it. Okay, so if we're factoring the numerator, it's a binomial. So I'm looking to see, well, there's not any squared terms, so really all I need to do is take out a common factor, right? What's common between 2 and 10? 2. So if I factor out a 2, what's left? X minus 5. So what if I factor the denominator? Multiplies to be negative 5 and adds to be negative 4. 1 and negative 5. So we have to find 3 things. We have to find horizontal and vertical asymptotes like we found last time we met. But now, this time, we also have to determine the removable discontinuities. Okay, so which one do you want to do first? Horizontal asymptotes. Okay, if we're looking at horizontal asymptotes, we look at the numerator. What's the degree of the numerator? The highest exponent of the numerator. It's a 1. What's the degree of the denominator? A 2. Are they the same? No. Well, if they're not the same, that automatically and obviously means that they are different, right? Which one is greater? The denominator. If the denominator is greater, does it have an asymptote, and where? Do you remember this chart from Friday? If the denominator is greater, the degree is greater, where's the asymptote? Y equals 0. Okay? And I'm going to be a little picky about that, because if you just put 0, I'm counting it wrong. 0 is just a number. It's not an equation of a line. No, it's y. But it's just y equals and not nothing. You see what I'm saying? You okay with that? Okay, so what about vertical asymptotes and removable discontinuities? Which one would be easier to get out of the way first? Removable discontinuities is easier to get out of the way first, because what am I looking for if I'm finding a removable discontinuity? Yeah, the same thing in the numerator and the denominator. Does the numerator and denominator have the same thing? Yes. So if I set that equal to 0, x equals 5. So does it have a removable discontinuity? Yes. Where? X equals 5. Very good. Last but not least, vertical asymptotes. Does this have a vertical asymptote? Is there a factor in the denominator that is not in the numerator? Then that's what I need to look at to see if there's a vertical asymptote. I picked up the wrong color, sorry. That's supposed to be blue right there. And my blue is dying. Set that equal to 0 and what do you get? Then that is my vertical asymptote. Any questions about that? Okay, then let's look at number 4. So what do we do first? Factor. Okay, so if I factor my numerator, somebody who hasn't factored yet. What? Very good. X minus 3, x minus 4. Somebody else who hasn't factored yet, factor the denominator. 6 and 2. I'll agree with that. Okay, so what do you want to do first? Horizontal asymptote. So what's the degree of the numerator? 2. Remember, degree is the highest exponent, right? What's the degree of the denominator? Are they the same or different? If they're the same, remember, we look at the leading coefficients. It doesn't matter what they are. That's what we look at. That's where we get our horizontal asymptote. What is this? A 1. What's this? A 1. So y equals? Yeah. If this was a 2 and this was a 3, what would my y equals be? 2/3, right? 2 over 3. If this was a 3 and this was a 5, what would my y equals be? 3 over 5. Does everybody understand that? Okay. So now removable discontinuities. What are we looking for? Same thing in the numerator and the same thing in the denominator. None. Yeah, that's it. There's allowed to be no removable discontinuities. Because if you don't have a common factor in the numerator and in the denominator, there's just not one. Okay? What about vertical asymptotes? How do you find those? Set the denominator equal to 0, right? So what's an asymptote? Where are they? Well, if I say x plus 6 equals 0, what does x equal? Negative 6. So x equals negative 6. But I also have this one. Wait, am I allowed to have 2 vertical asymptotes? Okay. X plus 2 equals 0, so x equals negative 2. X equals negative 2. Any questions? You have the idea of what to do on the other 4.